Good day, grade 12 learners. Welcome to today's technical sciences lesson. My name is Musa Zulu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Grade 12 again today, our knowledge area is still on wave, sound, and light. As we were last week again, still the topic, we're focusing more on light, but our subtopic for today will be electromagnetic radiation or electromagnetic waves. So that's going to be the focus there, subtopic of light, electromagnetic waves. All right, grade 12, our objectives today, what we expect that we must know by the end of this lesson is that by the end of the lesson, we are expected to be able to define an electromagnetic wave. We are expected to be able to explain the properties of electromagnetic waves. So you must be able to state and explain the properties of electromagnetic waves. And you must be able to discuss the electromagnetic spectrum. And you must be able to give some uses of electromagnetic radiation. Okay, so we should also be able to define what a photon of light is. And also we must be able to do calculations where we are calculating for energy of a wave, frequency, and wavelengths. All right. So we want to look at certain things that we're supposed to know when coming into this lesson, things that maybe we have learned in a previous grade or even in grade 10. So our pre-knowledge that we must come with in this lesson, grade 12, is we are expected to be able to define a magnetic field. You will remember that we started with magnetism in grade 10, and then we looked at magnetism in grade 11 as well. We must be able to look at electric fields. You would remember that we looked at electric field in grade 11 where we were looking at a charge, either it's a positive charge or a negative charge, where we said it has a region in space where a point charge, a 0.1 coulomb point charge, positive charge, that could be used to test that can either be repelled or attracted. You remember that, and then we said that region around that charge, we called it an electric field. So this is one of the things that we should just have an idea of going into electromagnetic waves. Okay, we should also remember to be able to give the constant value of speed of light in a vacuum. Again, well, something that we touched on last year in grade 11, that the speed of light in a vacuum. We've also looked at this last week when we were doing reflection and refraction, dispersion of light, and even lenses. We looked at the constant value of speed of light in a vacuum. And we should be able to give or even write down the formula to calculate the speed, the frequency, or the wavelength of light. You would remember that the formula will look something like this. Okay, all right. We should be able to explain what is meant by frequency, things that we also again looked at last week, be able to explain a wavelength, and we should be able to give the component colors of white light during dispersion. Again, some of the things that we looked at last week. So we'll come in with that knowledge to today's lesson. Okay, so to just ascertain whether people are able to give those definitions, we have just a small baseline assessment here with the questions as follows. Define the term magnetic field. Are you able to define the term magnetic field? Define the term electric field. Write down the value of the speed of light in a vacuum. Write down the formula to calculate the speed, the frequency, and the wavelength of a wave. Define the frequency. Define the term wavelength. And give the component colors of white light during dispersion. Right? Very, very simple questions that people should be able to answer. Your answers should be as follows. If you are defining the term magnetic field, you would remember in grade 11 we said this is a region in space where another magnet or a ferromagnetic material will experience a force of attraction or repulsion. We define the term electric field similarly to the term magnetic field. It is also a region in space in which an electric charge will experience a force again of what? Of attraction or repulsion. So here it's a magnetic or ferromagnetic material. Here it is an electric charge that experiences a force of attraction or repulsion. The other question was saying write down the value of speed of light in a vacuum. And the answer to that is the value of speed of light is 3 times 10 to the power of 8 meters per second. That's how fast light moves in a vacuum. Again, something that we spoke about last week when we were looking at refraction, reflection, and even dispersion of white light. Okay, we continue there. Write down the formula to calculate the speed or frequency of a wavelength. You would remember that last year we looked at this formula as the formula to calculate the speed of a wave. Okay, so this formula is going to become important for today's lesson and even going forward, grade 12. So we must remember the formula C is equals to F lambda, where the C was the speed of light in a vacuum. This was the speed of light in a vacuum, and then where the F represents the frequency of the wave, and where the lambda represents the wavelength. You would remember that this is what it was, the formula was representing. Okay, define the term frequency. We've defined this term again last week. We've defined this term last year in grade 11, the number of waves to pass a fixed point in 1 second. And then define the term wavelength is the distance between two successive points in phase. This is the distance between two successive points in phase. You would remember that a wavelength will look something like this, okay? The distance between two successive points. This is how we looked at a wavelength last year when we were doing grade 11. So you must remember that when we're speaking of frequency, it's the number of waves to pass a fixed point, right, in a second. So if you have a wave that looks like this, and then the waves start looking like this, this shows that the frequency is changing here. If you check here, there are a lot of waves that can pass a fixed point in a second compared to here. And even with this drawing, grade 12, it even shows the relationship between frequency and wavelength that we looked at last week here. To say, we said there's an inverse relationship between the wavelength and the frequency. I want you to check where the frequency is high. This is where I'm having a lot of waves passing a fixed point in a second. This is where I'm having fewer waves. So if I have more waves passing, I have a shorter wavelength, as you can see there in my diagram that I just drew here. But if I have less waves passing, I have a longer wavelength. That shows that inverse relationship between a wavelength and the frequency. Things that we must remember going into the lesson. And then the last question is asking us to give the component colors of white light during dispersion. We would remember that those colors, we say we remember them with this mnemonic Roy G. Beef, where the R stands for the red, the O stands for the orange, the Y is the yellow, the G is for green, the B is for blue, the I is for indigo, and the V is for violet. Each and every one of us should be able to remember these component colors of white light during dispersion. So we go, let us go straight to our lesson and start the lesson with this knowledge in mind, grade 12. Right, so the terminology that we are going to be exposed to for today's lesson, we are going to learn about electromagnetic waves. And we will say electromagnetic waves, definition there is changing magnetic and electric fields mutually perpendicular to each other at the direction of propagation of the wave. And again, I would emphasize, as I always do, this definition is taken from the examination guideline as it is. This is how we always want to define grade 12, we define according to the examination guideline. Okay, we're also going to learn about different types of waves or electromagnetic waves, such as we'll look at radio waves, we'll look at microwaves, we'll look at infrared light, we'll look at visible light, we'll also look at ultraviolet light, X-rays, and gamma rays. And then towards the end of the lesson, we are going to now focus on the photon. What is the photon? We'll learn another a new term there, a new terminology there, photon, which we will define as the quantum of energy. Photon is a quantum of energy. Right. So let's go straight into electromagnetic waves. Okay, so again, let's go back to knowledge in grade 11, where we said if we have a charge, right, that charge is going to have a region in space. So around that charge, there's going to be a region where a positive test charge will either experience a force of attraction or will experience a force of repulsion. So what we know is that if I have a charge, the charge will have a region around it that we will call an electric field. All right? Okay, so I want you to imagine with me here, grade 12, to say, if this charge, I were to move this charge, start vibrating this charge, which is what we said in grade 11 happens during the formation of waves, is that the particles are vibrating. They are either vibrating parallel to the direction of propagation or they are vibrating perpendicular, if you remember that. So if maybe this particle will start vibrating, say this particle starts vibrating up and down, let's say this particle is here, okay? It starts vibrating up and down. You will agree with me, grade 12 here, that the electric field of this particle, or the electric field around the particle, will start changing, right? I hope everyone agree with me that the electric field here will start changing, because if you look at the electric field, you remember the properties there, it's that the electric field is stronger, closer to the charge than it is further away from the charge. So if you are looking around this point here, you are going to have a strong electric field. But here, you do not have a strong electric field. But once the charge goes here, that means the electric field here changes, and then the electric field here also is changing. Now it's weak, now it's strong. Then we have a charge moving. So once you start having a charge moving, what are you going to be having? You are going to be having changing electric field, okay? So during electromagnetic waves, okay, or this movement of charge, they will then cause waves. They will cause a wave to propagate, okay? This wave or to propagate. This changing in electric field will then propagate as a wave. But then scientists found that this changing electric field will then automatically cause a change in a magnetic field. So this change in electric field will automatically cause a change in magnetic field. You remember that the particle is vibrating up and down, okay? This up and down of vibration will cause a wave to propagate perpendicular to the direction of propagation, okay? So the wave, the particles are moving like this, the wave is moving like this. So this, let's say this is the direction of propagation, okay? Then you have the particles that are vibrating up and down. So you are having a wave here propagating in this direction, but the movement of the particles, as we have explained this in grade 11, is up and down. Therefore, the movement of the particle is perpendicular to the direction of propagation. So for now, what is propagating is the electric field, or the changing electric field. This is changing electric field, propagating as a wave there. This changing electric field is going to cause change in magnetic field. And this change in this magnetic field is also going to propagate, but now it will propagate also perpendicular to the direction of what? Of propagation. But it will also propagate perpendicular to the changing electric field. So you are going to have changing electric field causing changing magnetic field. And this changing electric field and changing magnetic field are all radiating, right? They are all radiating as waves, okay, or propagating as waves. But they are propagating as waves perpendicular to each other. So you are having this one being perpendicular to this one, and still again perpendicular to the what? To the direction of propagation. So you are having electric field in this direction maybe, and you are having magnetic field in this direction, and you are having the direction of propagation in this direction, and all of them are perpendicular. So this is what this definition is trying to say to us, that there in an electromagnetic wave, that's when you are having changing magnetic and electric fields. They are mutually perpendicular to each other. So they are changing, causing each other. This one causes the other one. So the changing electric field causes the change in magnetic field. What the change in magnetic field again is causing the change in what? Electric field. So they are causing each other. So it's sort of like there is no sort of energy that is put into them. Both are giving energy to each other. This one causes the other one. So if we're having electric field here, or changing, let's say it's changing, not electric field, but changing electric field will cause changing magnetic fields. Magnetic fields, okay? While changing magnetic field is also again causing change in electric field. So they are causing each other. So they both propagate, and they propagate mutually perpendicular to each other, but they are also perpendicular to the direction of propagation. So that's why we define electromagnetic waves as what? Changing magnetic and electric field. They are mutually perpendicular to each other and the direction of propagation. Okay, so what I'm trying to draw here is grade 12 looks something like this. Okay, this is what we are talking about here. So here are the changing electric field. The changing electric field here propagating as a wave. This is where you are having the particles. Remember, the particles are vibrating. They are vibrating up and down. The particles are vibrating up and down. The wave propagates. Okay, energy being transferred. You remember that the wave is propagating, energy is being transferred to the particles. These particles give the energy to the next particle, to the next particle. Then the wave propagate, okay? But the wave is propagating perpendicular to the direction of propagation. This is the direction of propagation. This right here, our x-axis. I'll represent it with v for the velocity. This is the direction of propagation. And this is the direction of the wave, okay? And this wave is the changing electric field. This changing electric field will cause change or changing magnetic field. It will cause changing magnetic field, which will also propagate as a wave, but it will propagate as a wave perpendicular. If you can check here, we can create an angle of 90 degrees, which is why we are saying perpendicular. So it will propagate perpendicular to the changing electric field. So the changing magnetic field propagate perpendicular to the changing magnetic field, while both of them are perpendicular to what? To the direction of propagation. It is very, very important that we know this definition. We are able to write this definition if it is asked, and we also understand what is happening here, at least at a surface level. Okay, right. So if we can go back to our particles and think about it, there we were saying we are moving a particle, okay? A particle with an electric charge. It moves up and down. And what we know is that this particle is going to give us a wave that maybe sort of radiates outwards like this, okay? So, if we move this particle faster, what we are going to have is a wave that is going to have a higher frequency, okay? So, depending on how quick or how slow the particle vibrates, then this is going to then change the frequency of the what? Of the wave, okay? So the frequency of the wave will depend on how quick or how slow the particle is vibrating. If it vibrates quick, you are going to have higher frequency, okay? And if it vibrates slow, you are going to have a smaller frequency. Then that is going to give you different types of electromagnetic waves. So it means your magnetic waves are not going to be the same. You don't have the same wave. This wave here has longer wavelength. This wave here has shorter wavelengths. If you remember our wavelength, this one have longer wavelength because of its frequency. It's a smaller frequency. While this one has shorter wavelength because it has a what? It has a higher frequency. So that means depending on how fast the particles are vibrating, we will have different types of electromagnetic waves. And that is true. We do have different types of electromagnetic waves, and they depend on the frequency and the wavelength. these different types of magnetic waves that are created by the movement of particles, right? They have different types of frequency, and since they have different types of frequency, they have different types of wavelength. And since they have different types of frequency and wavelength, even themselves are different. So we have different types of electromagnetic waves, okay? And these electromagnetic waves can be arranged or are arranged or were arranged in what we call an electromagnetic spectrum. So an electromagnetic spectrum is a spectrum where we have an arrangement of electromagnetic waves, different types of electromagnetic waves that are different because of their differences in frequency, because of their differences in wavelength. If the particle vibrates faster, we expect that we are going to have a higher frequency. If it vibrates lower, we have a lower frequency. Then in that case, that tells us that we must be having different waves, because the wave that looks like this is not the same as the wave that looks like this. These two waves are not the same. So they must be given different names. Okay? So this is how the names can be arranged. They are arranged as radio wave as the first one, okay? And you have microwaves, okay? And it's important that you know these waves, and we've spoken about them at the beginning of the lessons. So we have radio waves, we have microwaves, we have infrared, okay? And then after infrared, we have visible light. And when we're speaking of visible light, we are speaking of the same light that we were talking about during dispersion. If you remember dispersion of light last week, grade 12. So we're talking about the same light or the same colors. And if you remember those colors, we said they are Roy G. Biv. Okay? And that Roy G. Biv says that we are starting with red. You remember that we are arranging them in terms of increasing frequency. So red had the lowest frequency there, and violet had the highest frequency. So just before we get to visible light, we have infrared. So these are electromagnetic waves before we can see red light. So I want you to just try and remember it like that. Infrared, visible light, and invisible light. What light or what color do you see first? You see red. So infrared closer to the red color of visible light. Okay, visible light, again we say, contains all these 7 colors from red all the way up to violet. Red, orange, yellow, green, blue, indigo, and violet. And just after violet light, you have again what is what? Ultraviolet. So again, infrared, red. Yellow, orange, yellow, green, blue, indigo, violet, ultraviolet. So these are the ways that we can just try to remember this electromagnetic spectrum and how you can arrange it. So you have wavelength, we have microwave, then we have infrared. Then infrared is followed by the visible, and the first light color that comes in the visible spectrum is red. Infrared, red. The last color that you are going to get is violet, and just after violet you get ultraviolet light. You get X-rays, and then you get gamma rays. Okay, this one is called visible light because it is the only electromagnetic wave that can be seen by a human eye. Okay, the other waves, electromagnetic waves, we cannot see. So we can't see radio waves, we cannot see microwaves, we cannot see infrared. Then we start seeing the red color all the way up to the violet color. Then after the violet color again, we cannot see the ultraviolet, greater than violet. Ultra, when something is ultra, it's at a level that is higher. So ultraviolet light there. Then we cannot see the X-rays, we cannot see the gamma rays. Okay, now as you can see here, this electromagnetic spectrum that I have here is arranged in a certain order. And what order is it arranged? Again, look at your waves. Okay, you have points in phase here. This means this is the wavelength. Just look at here, points in phase, this is the wavelength. So let's check the two wavelengths. You can see the wavelength is longer here, and you can also see here we are having a small amount of waves that are passing a fixed point here, But here we are having a large number of waves that can pass a fixed point in a second, telling us that here we have high frequency. So they are arranged in terms of increasing frequency. So it means here we have low frequency. This side we have low frequency. Okay, and going to the gamma rays, they have high frequency. So the radio waves have the lowest frequency. And again, if you try to think of what we were speaking about last week, we said red in the dispersion has what? Has the lowest frequency. Okay, so look at how it is even arranged here. The first color that you are going to be able to see is red with its low frequency compared to the other colors, of course, not compared to radio waves and microwaves. It has a low frequency compared to the other colors, and violet has high frequency, as you can see here. So the order in which these electromagnetic waves are arranged in this electromagnetic spectrum is in order of increasing frequency. Of course, you can also arrange them in order of decreasing frequency, but I like to arrange them in an order of increasing frequency, so that I start with the radio wave going all the way to the gamma rays. So it's important that you know the electromagnetic waves first. Know them: radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. It's important that you know them first. Then after that, you should know how to arrange them in terms of which one has the higher frequency and which one has the lower frequency. Radio waves have the lowest frequency, followed by the microwaves, followed by the infrared light, followed by the visible light, followed by the ultraviolet light, followed by the X-rays, and then with the gamma rays having the highest frequency then. So if the radio waves have the lowest frequency, you'd remember the relationship between frequency and wavelength. If they have the lowest frequency, that means they have the highest, or the longest, not the highest, the longest wavelength. They have the longest wavelength. Okay, your radio waves have the longest wavelength. The one with the shortest wavelength, as I was trying to show you here, are the gamma rays. The gamma rays have the shortest wavelength. The gamma rays have the shortest wavelength. So going in this direction, we are decreasing wavelength. Going in this direction, we are increasing wavelength. The wavelength is longer going in this direction of the radio waves. As you can see here, the diagram even says wavelength decreases as we go in this direction, but frequency increases as we go in that same direction. Okay? When frequency increases, grade 12, it increases with also energy. You would remember that waves are just a transfer of energy. You would remember that the particles are vibrating, but then while the particles are vibrating, they transfer energy, which is why we eventually end up having the wave, because it's a transfer of energy from one particle to the next. You would remember that the particles are not actually moving from one point to another point. They are just vibrating. That's why we're saying they're vibrating parallel to the they are vibrating perpendicular to the direction of propagation. The particles are vibrating, and then while they're vibrating, they give energy or transfer energy to each other. So one particle transfers the energy to the next particle, causing a wave of energy that is being transferred then. So the more frequent the particles are vibrating, then the higher the energy that is being transferred. So that means in this direction, as we increase frequency, we also increase energy. So energy increases with increase in frequency. So it's very, very important to know that. It's not part of my diagram here. Okay, so let's say here, let me put it here and say increase in energy. So energy increases here. So energy increases with increase in frequency. Okay, so it means where we have low frequency, we have low energy. So that means the radio wave will have the lowest energy. okay, followed by the microwaves, infrared, visible, ultraviolet light, X-rays, and gamma rays. When it comes to energy, the radio waves will have the lowest frequency. They will also have the lowest energy, while the gamma rays will have the highest frequency. They are also going to have the highest energy. Okay, the radio waves will have the longest wavelength. Okay, they will have the gamma rays will have the shortest wavelength. Okay, so we remember that wavelength increases going to the radio waves, but frequency increasing going to the gamma, and increase in frequency will cause an increase in energy. Okay, right, so these waves, when they propagate, they have properties, okay, under which they propagate. Okay, the following properties are the properties that you must know, grade 12, because these properties can be asked. They usually like asking, the examiner usually like asking the properties of waves, to say how do these waves propagate. Okay, the waves can propagate in a vacuum, okay, and the waves can propagate in a medium. Okay, these waves do not necessarily need a medium to propagate. If you remember, even though they are light, we are talking about light. If you remember last time, we said light needed a medium to propagate. Okay, light that we were talking about last week. But not all light need visible light that will need a medium to propagate through. But not all light need a medium to propagate through. Okay, these electromagnetic waves can propagate in a vacuum, in an empty space, a vacuum. But they can also propagate in a medium. Okay. And how do they propagate? They will always propagate in the speed of light. And the speed of light in a vacuum will be c is equals to 3 times 10 to the power 8 meters per second. So they propagate in the speed of light in a vacuum. This speed of light obviously will decrease as they enter a medium. It decreases a little bit, okay? Okay, so depending on that medium in which they will be propagating it, but however, they will still be propagating at that speed of light. Okay, so they always propagate in the speed of light, or in the speed of light. Okay, number two, they transfer energy. Like we've been speaking, that for us to have the wave, the particles are transferring energy. So the electromagnetic waves, they transfer of energy. And like we said, the amount of energy transferred is determined by the frequency of the electromagnetic wave. Okay, we should be able to know the properties, and we should be able to explain the properties, grade 12. So the electromagnetic waves, they transfer energy, and the amount of energy that is transferred is determined by the frequency of the electromagnetic wave, as we say. If we have higher frequency of the wave, then we are going to have higher energy being transferred in that particular wave. Okay, this is what makes some of these waves dangerous. Okay, this is what makes some of these waves dangerous to be around. Okay, you don't want to be exposed to gamma rays. When I'm teaching, I always make examples of movies and say, in the Marvel movies, they always say Hulk was exposed to gamma rays. That's why he changes and becomes this big blue green monster, because he was exposed to gamma rays, which are electromagnetic waves that a human being is not supposed to be exposed to. So was exposed to too much frequency of these waves and a large amount of energy. That's why it causes him to just turn and becomes like a green monster, like he becomes. You'd remember that Spider-Man also, for him to turn and become a spider, he was bitten by a radioactive spider, they say. So that means the spider had radio waves in it. He was bitten by those things. So we do not want to be necessarily exposed to these waves, electromagnetic waves, because they can be dangerous. The amount of energy that they carry can be dangerous. Okay, their danger differs depending on the energy. It's if you are exposed to radio waves, it's not that bad. Okay, as I go back to my waves, if you are exposed to these waves, it's not that bad as being exposed to the gamma rays, because if you are exposed to gamma rays, the gamma rays have high energy. The energy of the gamma rays is so high that it can penetrate through a lot of things, like penetrating through the skin, can penetrate through our skin. And if it penetrates through the skin, it can penetrate and it can actually attack the cells, and it can even cause cancer. Okay, it can even cause cancer. Not only the gamma, also the X-rays, also the ultraviolet light, also the infrared light, the microwaves, even the radio waves themselves. If you can be exposed to too much of a wave, then, however, just being exposed to gamma rays, okay, the amount of gamma rays needed to cause maybe cancer is not the same as the amount of radio wave that is needed. Okay, so you can be exposed to radio waves for some time and not get cancer, but if it happens for a long period of time, you are exposed to these radio waves, there is a possibility that you might get because of the energy. But because the energy there is usually small, it might take a long time. But it will not take the same amount of time if you are exposed to gamma rays, because gamma rays have high frequency and they have extremely high energy. So it will not take the same time. It will take a short amount of time with gamma rays for them to penetrate through your skin and start killing off the cells there, causing cancer cells in your body there. Okay, so we are talking about how they transfer energy. One of the properties, they transfer energy. So number 3, another property is that these electromagnetic waves are polarized, and by this we mean they are just transverse waves. They are transverse waves. If you remember last year, we spoke of a transverse wave as just a wave, not in practicality. We spoke of longitudinal in grade 11, and in practicality we spoke of longitudinal in terms of sound waves, but we also spoke of a trans wave, not in practicality. The practicality of a sound wave is that it is light now. Not a sound wave, but a transverse. A transverse wave is light. It's electromagnetic waves. Okay? Electromagnetic waves, number 4, there says that they are dual in nature. Okay? They propagate in the speed of light. They transfer energy, and the amount of energy they transfer depends on the frequency of the electromagnetic waves. They are polarized, or I like to say they are transverse. Instead of saying they are polarized, I'll just advise people to just say they are transverse. Okay? Okay? And then number 4, they are dual in nature. They are dual in nature. And what do we mean by they are dual in nature? Light, okay, can behave as both as a wave and as a particle, depending on the circumstances. So electromagnetic waves is dual or are dual. Okay, they can behave one as a wave, and then sometimes you can find them behaving as a what? As a particle, depending on them, on the circumstances. So it's important that you know these properties, grade 12, that you are able to state the properties and give the properties if the question is asked. Give the properties of electromagnetic waves. You just say they transfer energy, they transfer energy, they propagate in the speed of light, they are dual in nature, and they are transverse waves. Right, so those are the properties of electromagnetic waves. Let's look at the uses of electromagnetic radiation or electromagnetic waves in our everyday lives. Okay, as we said there, our spectrum consists of, as how I like to just simply abbreviate it there, I always write RW, MW, infra, and then I write Roy GBIV, and then I write UV, then I write X, then I write gamma. Okay, so that's how I usually abbreviate it. So each and every one of these, they have uses in our everyday life. And this part here, grade 12, I will be honest with you that it's a bit tricky because there are a lot of uses even myself, that I cannot know all of them. So there are a lot of uses. So what I would advise you to say is just know a couple of them so that you can be able to answer questions. Just know a couple of uses per electromagnetic waves. So in case you are being asked, write down the uses of radio waves, you know at least 3 or you know 4 for each electromagnetic radiation or electromagnetic wave, because there can be a lot that can be counted there. A lot of things that can be counted. I will count what I have, and I might be counting something here, but you also have an idea of something else that I did not put in here. But there could be a lot of waves, of uses, I mean, of these waves. So we'll start with radio waves and say, how are radio waves used in our everyday life? Well, radio waves are mostly used for communication. Grade 12. They are mostly used for communication, for such things, for things such as television, and since they are radio waves, you find them in radio, okay, and then radio telescopes. They are used in wireless networks, okay. They are used in GPS or navigation systems. They are used to for garage door openers. They are used in police radios. They are used in toys, etc., etc. It could be a lot of uses there. Okay. Let's go to the next one. Microwaves. Okay. Some of the examples of microwaves. If they say microwaves, and I am sure to everyone immediately they hear that microwaves are electromagnetic waves, they were surprised because they thought microwaves are these ovens or these appliances that they use at home. Okay, those are actually microwave ovens. They are called microwave ovens. They are called microwave ovens because they use microwaves. Okay, they function using microwaves. The microwaves is a form of light. It's an electromagnetic wave. Okay, so microwaves are used in microwave ovens. Okay, and microwaves are also used in a radar system. Microwaves are also used in Wi-Fi, which is wireless networks. Again, so one thing you would notice about radio waves and microwaves is that they are closely related. Most things that are that you get from radio waves, you also get having microwaves. Most things that have microwave, you also get having radio waves. So they are closely related. Both of them are mostly used for communication, because you would find satellite as well. As you see here, there's a satellite with radio waves. You'd also find satellites. Here we are talking wireless network. Here we are talking Wi-Fi, which again is what is a wireless network. So microwaves and radio waves have that close relationship, and it is because they are close to each other, as you saw with their wavelength there and frequency. They both have small frequency, but they have longer wavelength because both of them, I mean to say them. As we move on them and look at uses of infrared light, okay. Again, here I always take people to make examples of movies. Growing up, there was this movie starring Arnold Schwarzenegger, where we were watching the movie that was called Predator. And then whenever you see the perspective of the predator, well, it was hunting them down there. The image that looked like this is how the predator was able to hunt them down. This is how it saw them. To them, this is how they looked. And they were radiating, I now know that to the predator, they were radiating infrared light. That is why the predator was seeing them like that. What they were radiating was infrared light. So one of the uses of infrared light there is thermal imaging. But it is not only in that movie. A lot of movies where you would find armies or soldiers going into war at night, and then they start putting in these night goggles there, where this is how they see at night. they look at things and things are radiating those infrared light there. Then that's how they see. Those night goggles are using infrared light. That's why they see like that. Okay, so night vision goggle, as you can see here, it is also using for cooking purposes, especially in restaurant, and it is also used in remote control. Infrared light is also used in remote controls, and it is also used for short range communication. Again, I'm pretty sure that I have not counted all the uses of infrared light. You may know more than what I have counted there, but the idea is that know and have an idea of a technological uses of infrared light. Okay, what are the uses of visible light? Well, mostly is for us to see, because we can see visible light, we can see those colors, but it is also used in photography, it is also used in optical fibers. If you remember, we spoke about optical fibers there when we were talking about total internal reflection last week. Okay, and during that total internal reflection, we have light that is passed through an optical fiber. Okay, and all that light is a visible light. So those are the uses of visible light. Visible light is also used by plants during a process called photosynthesis. You'd remember this process that you definitely sure that you looked at in grade 8, where you're looking at a process of photosynthesis, which is a process that needs sunlight. It is a process that needs sunlight. So those are again just some of the uses of visible light that we can be aware of or know grade 12. Okay, let us continue there and look at the uses of ultraviolet light. Okay, ultraviolet, again, a lot of uses there, right? One I like the most, ultraviolet light is used to detect counterfeit note or fake note. It is used to detect counterfeit or fake notes, money. It is used to detect fake money notes. Okay, so say if you have fake notes or counterfeit notes, then you can use a ultraviolet light there to detect whether this money is fake or not. Okay, another use that is not there in my picture, ultraviolet light is also used to sterilize hospital equipment. It is also used to sterilize hospital equipment. As I said there, I'm thinking of this one right now. It's not even part of my picture. That's why I was saying there is a lot of uses that can be there. Okay, there are a lot of uses that I am not counting here. Again, you think that ultraviolet light is used a lot. I personally myself that I learned this last week that ultraviolet light is used by when people are doing bath and shine in the salons. I myself did not know that, but when people do bath and shine, apparently there's a machine where they put their hands in there and then it uses ultraviolet light. I am still to confirm that, but this is what I got from my learners this previous week. So there are a lot of uses of this ultraviolet light. It could be more than what I'm telling you right now. You might know a lot. Okay, so we go to X-rays there. What are the uses of X-rays? Well, the most important one is again in hospital equipment there. That X-ray is used to penetrate the skin, right? To penetrate the skin, to check for broken bones, to check for broken bones. Okay, all right. Now again, to just talk about the issue of high energy, because now we are talking about electromagnetic waves that have high energy, and to emphasize the issue of these electromagnetic waves that have high frequency, will have high energy. You would notice if you've been to hospital where someone or or yourself, right, have been put in an X-ray machine. when the doctor has to put you in there, the doctor cannot be there inside the same room with you. They will put you in there and then they will leave. They will only analyze the images that they get from there. And again, the reason is that the doctor cannot be exposed to the X-rays waves for a long period of time. Because remember, the doctor puts in a lot of people there. How many people does the doctor see a day? 3 or 4 people that he has to put in that X-ray machine every day. If he is in the same room as every patient, it means he's exposed to these electromagnetic waves every now and then. And if he is exposed to these electromagnetic waves, they can be dangerous to him because they have high frequency and they have high energy. They have high energy that is so high that it can penetrate through the skin. That's how high the energy they have. They have energy that is so high that it can penetrate through the skin. As it says there, X-rays have higher frequency than UV rays do. Therefore, they carry more energy. They can penetrate most matter, but not bone or lead, right? So they do not penetrate the bones. That's why we can see the broken bones. They penetrate through the skin. So they are used in medical equipment there. Okay, they are used in medical equipment to penetrate the skin to check for broken bones. Another one that I'm just thinking of right now, X-rays are also used in security systems. In security system, they are also used in security systems, especially in airports, where you would have, they will put in a bag and then they will have a monitor there where they are looking inside the bag without actually opening the bag, because it can penetrate through most matter. As it says here, the X-rays can penetrate through most matter. It does not penetrate only through the skin, it can penetrate through other things as well, such as backpacks. So they will just put in your bag and your bag will go through the X-ray, and then they will just see on the monitor as the X-rays are penetrating through, and things that are inside the bag can be visible then. Okay, so things that are inside the bag can be seen there through the X-ray. So this is another use. It's used in medical equipment. It is also used in security system. So again, it's emphasizing the point of saying that these uses are a lot. There can be a lot of uses of these electromagnetic waves. Okay, as we go to the last one there. Okay, some of the uses of gamma rays again, like the infrared was giving that night vision. These ones, they can give us what we call medical imaging. Okay, this is where gamma scan is obtained by injecting a radioactive tracer which concentrates in the area of the body being investigated. So it will concentrate in a specific area. The gamma rays emitted from this area are detected by the gamma camera. So the gamma camera is the one that is going to give us medical imaging. Remember, grade 12, you don't need to do all of these explanation. If you are asked, you will just simply be asked for uses. All you have to do is saying medical imaging. Okay, like the ultraviolet light, gamma rays are also again used for sterilizing hospital equipment. So gamma rays are used to sterilize medical equipment because they are highly penetrating and kill all living cells. Highly penetrating, and they kill all living cells. So in hospital equipment, before maybe they can perform surgery, they do not want to have a equipment that has living cells where it can cause infection to the patient. So they kill all living cells by sterilizing the equipment using the gamma rays. Either they can use the gamma rays or they can use the ultraviolet light. They can both sterilize the equipment there. They are also used in industrial imaging, right? Here's a gamma rays are even more penetrating than X-rays. That's why they are more dangerous than X-rays. They have more frequency than X-rays. They will have more energy than X-rays. So they will are more penetrating again than what? Than X-ray. They can pass through denser material that an X-ray cannot pass through, and they can be used to examine metal castings and welded structures. So they can be used to examine those things there in industry. So those that again is our use there, grade 12, as we are people in technology. We are people in industry. So we are talking about welding there. We check welded structures. We check metal castings there. We can use industrial imaging, which uses gamma rays. So those are the uses of electromagnetic waves, grade 12, that we want to be familiar with them. All right. Okay, so let's move from electromagnetic waves as a wave and electromagnetic spectrum that we've spoken about there and the uses of electromagnetic. And then let's look at a photon now. Okay, because we said light or electromagnetic waves are dual in nature. They can be a wave, and then they can also be a what? A particle. Okay, so when we look at them as a particle, we look at them as a photon. Okay, and we say a photon is a what? A quantum of energy. Okay, so photon, when we're talking about a photon, we're just talking about a quantum of energy. Okay, so what we just need to know here, grade 12, we don't want to complicate a lot of things. We just need to know this definition that a photon is a quantum of energy, and we simply need to know how to calculate this energy, the energy of a photon, okay, or the energy of a wave. Okay, so we just need to know that a photon is a quantum of energy, and we just need to know how to calculate this. And it is calculating using the formula E is equals to HF, okay, where E represents the energy and will be measured in joules. That will be the SI unit of the energy, okay? And then F represents the frequency, as we've spoken about it. And the SI unit of frequency, remember, is hertz, okay? And then we have this H here. This H is a constant value, like we had constant value for C, the speed of, the speed of light. This H here is also a constant value, which is what we call Planck's constant. So this is Planck's constant, a very, very large number that has been, or a very, very small number, let me put it like that, very, very small numbers with a lot of digits, I should say, right? That has been rounded off in this case. And it has been rounded off to 6.63 times 10 to the power minus 34. That's the constant value of Planck's constant. Now, grade 12, you don't need to worry about these and start saying you need to memorize it. Even though myself, I always advise people to know it. That's what I always emphasize to learners. I say, know it, okay? As much as I tell you that it will be given to you in your data sheet during exam, it should be given to you, this Planck's constant, but you must know it, okay? Because what if you don't see it there? What if you are panicking so much that you think it's not there, and then you don't see it? But if you knew it, you will just remember it. It's not difficult to just memorize 6.63 times 10 to the power negative 34 as Planck's constant. Okay, so if you know Planck's constant, then it is simple, it is easier for you to calculate the energy of a photon. Okay, right. So that means for me to be able to calculate the energy of a photon, I must know the frequency of the wave. Okay, so I must know the frequency. Given the frequency of a wave, I can calculate the energy of a photon. So what if I don't know the frequency of the wave? Is it possible for me to calculate the energy of a photon? And the answer is yes. If I don't know the frequency, but maybe I know the wavelength of the wave. I don't know the frequency, but I know the wavelength of the wave. Is it, am I stuck now? Will I not be able to calculate this energy? The answer is no. I can still calculate the energy of a photon there. How? Take you back to that formula where I said you are going to need the formula C is equals to F lambda, because this formula creates a relationship between C, which is the speed of light in a vacuum, and then F, which is the what? Which is the frequency. So we need this formula. And this formula looks something like this. It's C, the speed of light, which is 3 times 10 to the power 8 meters per second. Okay, and then lambda, which is wavelength, measured in meters there, and then we have the frequency, which is measured in hertz. You would remember that we know this formula. Okay, right. Now, if I decided to make F the subject of the formula, because remember, my original formula says E is equals to HF. Now, what if I have a problem that I don't have the F, the frequency, but I have the wavelength? What can I do? Well, according to this formula, I know that I can write the frequency C is equals to F lambda. I can write the frequency in terms of wavelength and speed of light by dividing by F on both sides of the equation. This is going to cancel this, right? This is going to cancel this, okay? And I will have here, or remember, we're looking for F, okay? So I'm making a mistake there. C is equals to F lambda. I should actually be dividing by lambda because I want to make F the subject of the formula. This cancels this, then I have F is equals to C over lambda there. So now I have frequency, okay, in terms of speed of light and wavelength. The frequency is given by C over lambda. So now I can jump to this formula and say this formula is E is equals to HF, but I do not have F, but I do have the wavelength, and I do have a relationship between wavelength and frequency there that says they are inversely proportional for a constant speed of light. So instead of writing this F here, I can come and substitute the F and write it in terms of the relationship between frequency and wavelength for a constant speed of light. And say H, instead of F here, I write C over lambda. Where if I simplify and multiply out, I'll get H times C will be HC over lambda. Giving this shortened method of calculating for energy if given the wavelength, if I do not have the frequency there, grade 12. So if it happens that I am not given the frequency, I can still calculate using this shorter formula. Okay. However, you do have the option of calculating using first this formula, just use it, calculating using numbers, then going back and substituting to this formula. That is still an option. A longer way, this one is a shorter way of doing it. Okay, just using these formulas. All right. Okay, let's look at an example of calculating this energy, grade 12, and see if we are able to do such. Okay, so here's example 1 says here, calculate the energy of a photon with a frequency of 3.2 times 10 to the power 10 hertz. So for this one, it's easy. We are given the frequency. So how are we going to calculate? Well, first, we need to write down the formula. It is extremely important, grade 12, to always make sure you write down the formula correctly according to what is given in a data sheet. So it should appear like this. E is equals to HF. Okay? Where E represents the energy, H Planck's constant, F is our frequency. Then you say, what is my H Planck's constant? 6.63 times 10 to the power minus 34 multiplied by the frequency of the photon, which they say is 3.2 times 10 to the power 10. What is the energy of this photon? The energy of the photon is going to be, we're saying 6.63 times 10 to the power of negative 34, and then we are multiplying this by 3.2 times 10 to the power of 10, and then we should get that the answer is the energy there will be 2.12 times 10 to the power of negative 23 joules. Okay, 2.12 times 10 to the power of what? A negative 23 is the energy that this photon has. Okay, we've been able to calculate it. And this was simple, grade 12. This was simple formula, substitution, and answer. Not even one learner should ever get this wrong, grade 12. You have the formula, you substitute in the formula, and you get the answer. Not even one person should ever get this wrong. Okay, let's look at example 2, right? And try to make it maybe challenging and see if it could be challenging there. Okay. Right. Instead of example 2 there, grade 12, we're going to take an activity there for just 4 minutes and see if you are able to do the calculations that we are speaking about. Then maybe after the activity, we'll work on another examples looking at time. So let's take 4 minutes and check if you are able to answer the following questions there. So grade 12, your time starts now. Welcome back, grade 12. I hope the time given was enough for you to calculate and also answer the other questions in our activity. Right. So our activity, it's an activity straight from a previous question paper there, grade 12. As you can see there, question 9 from a previous question paper, where they were saying in 9.1, define a photon. And we have looked at the definition of a photon there, a simple one, just a quantum of energy. Number 2 there was saying, identify the type of electromagnetic waves that is applicable to the function or use depicted in each of the pictures alongside. Write down the name of the electromagnetic wave next to the letter H in H. You can say it's visible light waves, if maybe you think it's invisible light waves. So you would see here the pictures here, TV remote control, and then here taking pictures of broken bones. What do you think is the electromagnetic waves there? Turning on sunbeds, and then nuclear explosion, telecommunication, and even cooking there. So what do you think is the type of waves that are there? For TV control there, I'm sure, and I hope everyone saw there, and they said these are infrared light waves. These should be infrared light waves. And then for P here, again, sort of obvious there, this is X-rays, okay? These are X-rays waves, okay? Okay, I hope everyone it was just clear to everyone there. And then turning there on the sound bed there, okay, this is UV light, okay? This is UV light, okay? The one that is applicable here. We have 1, 2, 3, 4, 5, 6 there. We have 6 pictures there, so it's enough to give one per picture there. And then for the nuclear explosion here, if you are having a nuclear explosion, the types of waves that you are going to be having there mostly would be the gamma rays. It would be the gamma rays there. And then for E, it could be gamma rays, it could also be X-rays there. Let's say gamma rays or X-rays. You can also find X-rays there. Okay, for E there, telecommunication, we have satellites there. So telecommunication, what waves are we talking about there? There we are talking about radio waves, or we are talking about microwaves. So you can put in radio waves or microwaves. So I'll take radio waves for now because I already see microwaves here. Cooking food here, it is an oven. So here you are going to have microwaves when we are cooking food there. So these are the electromagnetic waves that can be of use in these applications that or appliances that are there. Okay, so let's look at the next part of activity 2 there, where they were saying calculate the wavelength, or they're saying the wavelength of one of the waves is 600 nanometers. Okay, 600 nanometers. Calculate the energy of its photon. They want the energy. NM here, grade 12 stands for nanometers. You'd remember in grade 10, grade 12, that we looked at SI prefixes, right? Those SI prefixes that you are supposed to know, where we said times 10 to the power minus 3 is milli, okay? Times 10 to the power minus 6 is micro, times 10 to the power minus 9 is nano, times 10 to the power minus 12 is pico. Each and every one of us should know these SI prefixes, grade 12, especially when we have to deal with waves. Again, these we were exposed to in grade 11 we were doing waves. Milli, micro, nano, pico. And they go 3, 6, 9, 12. Okay? You also have the bigger ones, the kilo, the megas, the giga, and the teras. Okay, but for now, the ones that are most applicable here, because we're talking with very, very small distances here, we're talking meters, we're talking nanometers, millimeters. It's actually usually nano. It could also be pico there. So you have a wave of 600 nm stands for nanometers, and nanometer is a SI prefix that represents times 10 to the power of a negative 9 there. That's the first thing about this question. Number 2, this question wants us to calculate energy. However, we are given wavelength, not frequency. Okay? The first formula that we know of energy is E is equals to HF, where we need Planck's constant and the frequency. However, this question is asking us to calculate using a wavelength. So how are we going to calculate using wavelength? This is where that formula that I was trying to show you comes in handy. Okay? To take a shortcut here, you can just simply say E is equals to HC over lambda. E is equals to HC over lambda for wavelength, where you are just going to simply substitute H, Planck's constant, 6.63 times 10 to the power minus 34, multiply that by C, which is the speed of light in a vacuum, 3 times 10 to the power 8 meters per second, divide all of that by the wavelength which they've given you, 600 times 10 to the power negative 9. Now, do you see here, grade 12? If you don't know what Nm is, you have lost marks here, which is unnecessary. This is marks lost, unnecessary, grade 12, and this is not something that should happen, because just know the SI prefixes, okay? Because most of you, maybe when you are attempting this, you probably did 600 without putting times 10 to the power negative 9. I hope that is not the case, because if that is the case, that means you are giving away free marks. These are free marks. So 6.63 there, 6.63 times 10 to the power of a negative 34 multiplied by 3 times 10 to the power of 8 all over 600 times 10 to the power of a negative 9. Okay, what do we get there? We get that the energy is 3.32 times 10 to the power of negative 19 joules. That's the energy this photon has. That's the energy of the photon of this wave. The energy of a photon of this wave is 3.32. Now, however, grade 12, you could have done this like this by writing C is equals to F lambda, right? And then you substitute C is 3 times 10 to the power 8 is equals to, you don't know the frequency, multiplied by 600 times 10 to the power minus 9. Then from here you solve for the frequency. Then after you have solved for the frequency, you then take your frequency, you substitute it in that equation there. That was another possible way. It's a longer route, but it's also another possible way. This one is just shorter. Okay, so if we do 300 or 3 times 10 to the power of 8 all over 600 times 10 to the power of negative 9. Negative 9, we should get the frequency of 5 times 10 to the power 14 hertz. Okay, and then from that frequency, we can now then come here and say E is equals to HF. We now have the frequency, H is 6.63 times 10 to the power minus 34. We are multiplying this by 5 times 10 to the power 14, which is the frequency that we calculated here. And then let's do that. 6.63, multiply that by 10 to the power of negative 34. That must be multiplied by 5 times 10 to the power of 14, which is your frequency. Again, you get exactly the same answer, 3.32 times 10 to the power minus 19 joules of energy. But you see, this one was a multi-step question because you needed to do this calculation first before you can do this calculation. But this formula here just simply saves you time and gives you a shortcut. And whichever way you choose, and I advise you to choose the way that you prefer the most, stick to the way you prefer the most. In this case, you don't necessarily need to go to the or listen to me. Stick to the one that you prefer the most and stick to it and master it, and make sure that it always gives you the marks that you are expecting there. Okay, so that was our activity there, grade 12. And again, these are the solutions that we were talking about. Define a photon, quantum of energy. There it was infrared light, it was X-ray. There we had ultraviolet light there. And there it was either gamma rays or X-rays. On the other one, it was radio waves or microwaves. On the other one, we also had radio waves or microwaves. And then in the calculation of 9.3 there, we had 6.63 there, substituting there as Planck's constant multiplied by C, which is 3 times 10 to the power 8, over 600 times 10 to the power minus 9, which is what? Nanometers per second. And you get your answer like that. Okay? All right. So, grade 12, let's look at the summary for today. Things that we have looked at and considered. Okay, grade 12, we want, or you should be able to define an electromagnetic wave. Okay, you should be able to explain the properties electromagnetic waves changing electric and magnetic field mutually perpendicular to each other and the direction of propagation of the wave. That's how we defined it. And then we should be able to explain the properties of electromagnetic waves. Okay, they propagated at the speed of light. They transfer energy. The more the frequency, the more the energy they are transferring. They are transfers. Instead of saying they are polarized, I would prefer that people say they are transfers. I think it's easier to remember that way. But however, if you remember they are polarized, still fine with me. And they are dual in nature. Okay? And if you say they are dual in nature, it means they behave as both a particle or a wave, depending on the circumstance. You should be able to give uses of electromagnetic radiation. My advice to you is that each electromagnetic radiation or each electromagnetic wave, you must know at least two. Each electromagnetic wave, you must know at least two uses of the electromagnetic wave. And then you should be able to define a photon as a quantum of energy, and you should be able to calculate the energy frequency and wavelength. And remember, when you're calculating, you're using a formula E is equals to HF. But again, there's another formula of E is equals to HC over lambda. In which case, here, that is when you are given only the wavelength in your question. If you're only given the wavelength, the best formula to use is this one. However, you can also go through this formula, C is equals to FH. Okay, right. Again, you should be able to again to discuss the electromagnetic spectrum. I skipped this one here in my summary. You must be able to also discuss the electromagnetic spectrum. One, arrange the electromagnetic waves. You should be able to arrange the electromagnetic wave. Shorter summary of electromagnetic wave, always put them like this: RW, MW, infra, visible, or Roy G. Biv. That's Roy G. Biv. Okay, X-ray, and then gamma. This is just a short summary of the electromagnetic spectrum. Electromagnetic spectrum has radio waves, and there are 7. 1, 2, 3, 4, 1, 2. Oh, I forgot ultraviolet light here. Now I don't have 7. UV. Okay, now there should be 7. 1, 2, 3, 4, 5, 6, 7. Okay, so you have ultraviolet light there after the Roy G. Biv or the visible light. Okay, Roy G. Biv is for visible light, by the way. That's the visible spectrum. Okay, then you should also remember that going in this direction, they are increasing frequency. Their frequency increases as we go in this direction. Okay, and then going in this direction, here we are increasing wavelength. We are increasing wavelength, lambda, going in this direction. So the radio wave again have the highest wave, the longest, the highest, the radio waves have the longest wavelength, while the gamma rays have the shortest wavelength. But the radio waves have the lowest frequency, while the gamma rays have the highest frequency. While frequency is increasing, an increase in frequency will cause an increase in energy. So it means here they increase frequency and they increase energy going in the direction of the gamma rays. So being able to discuss the electromagnetic spectrum in terms of wavelength and frequency like that, you need to be able to do that. And just summarizing it quickly like this, grade 12 can help you a lot when you are writing down your notes and you are studying through the electromagnetic waves then. So you should, these are the things that you should be able to do grade 12. Okay, right. And for your homework there, another previous question paper that or question that is taken from a previous question paper there is just questions like here: state 2 properties of electromagnetic waves. Okay, what is a photon? Write down the name of the type of electromagnetic waves in the answer book. As you can see there, the diagram is showing them. And in this diagram, they've even helped you there with lowest frequency, highest frequency there. As we're saying, which one of the electromagnetic waves above has the shortest wavelength? Okay, name 2 uses of X-rays, and then calculate the energy of a photon of a microwave with the frequency of this. This one has frequency, or this one looks exactly like the one that we were doing there in our example. Okay, we have 2 homeworks there. Here's another one again taken from the previous question paper there. It says define the term electromagnetic waves. And then the electromagnetic spectrum consists of the following electromagnetic waves. They've put there in no particular order: ultraviolet rays, microwaves, X-rays, gamma rays, radio waves, infrared. And they want you to arrange them which electromagnetic wave has the longest wavelength, or they're asking which one is the longest wavelength. You should be able to answer this question there in your homework from that summary, small summary that we have. Which one has the highest frequency? Very, very simple question there. Then this one, a photon of blue light has an energy of 1.75 times 10 to the power minus 48 joules. Determined by means of calculation whether a photon of light with a frequency of, so that means now we're speaking of a different photon of light. This one has a frequency of 7.50 times 10 to the power 14 hertz, is the photon of green light or indigo. Okay, so it means you are going to calculate that energy and you are going to compare with the energy of blue light, and then you are going to remember Roy G. Beef there. Okay, so if they tell you that the energy of blue light is this much, okay, whatever energy you get there, they are asking, is it green or blue? If the energy is high, is it green or indigo? I mean, if the energy is higher than this one, then it must be indigo. But if the energy that you get when you calculate is smaller than this one, then it means that light is green. I hope you get how I'm just trying to give you a clue as to how to answer 10.3 there, as it seems like it could be a little bit tricky. So you just simply calculate the energy of this photon that is unknown whether it's green or it's indigo. But how do we determine whether it's green or indigo? We compare the energy to that of blue light. They say it can either be green or indigo. And green and indigo are between, blue is between green and indigo. So if it's higher, as we know that we increase energy going in this direction, it will be indigo. But if it is lower, as we know that energy is increasing only going in this direction, it should be then green. Green has a lower energy than blue light, and indigo has high energy than what? Than blue light. So that is how you would want to attempt this question right here. Now, grade 12, do not forget to join us again next week, same time from 2:30 up to 4 o'clock, 23rd of May. We're going to be starting a new topic there, elasticity and hydraulics, going back to mechanics there. Grade 12, thank you.